Hey there, pre-calculus. I've got a video for lesson 5.7 in which we talk about very similar problems to 5 as we saw in 5.6, but instead of using the split up the triangles method, I'm going to show you guys something called law of sines and law of cosines, which can be quite helpful and quite convenient. So what I'm going to do is I'm going to explain how law of sines comes about, and then I'll just say what the formulas for law of cosines are because they're a little bit more involved. So if you have a generic triangle, it's not a right triangle in which the angles are listed as A, B, C, and the opposite sides to each angle is just listed as the lowercase variable of that choice, we can come up with some, just through investigation of splitting up this triangle, you guys will see how we can come up with maybe a better approach to solving for parts of these triangles. So let's say that we drop an altitude from angle B to side B. Well, that gives us the sine of A is going to be the height divided by C. And the reason why I'm even putting this up here is because we have a very similar equation on the other side. The sine of C is equal to H over A. And the reason why that's significant is, by the way, that's H. The reason why this is significant is because what we can do is we can say multiply both sides of this equation by C, multiply both sides of this equation by A, and now they both equal H, which means they equal each other. So C times the sine of A is equal to A times the sine of C, which through further algebraic manipulation, what I can do is divide both sides by A, canceling it out on the right. Now the A's are reunited, so to speak, and then you can divide both sides by C. And then the C's are reunited. So this is really helpful if we have diagonal information. If we have 3 out of the 4 pieces of information of diagonals, what I mean by that is the angle with its opposite side, we're in good standing here. So the sine of A over little a is equal to the sine of C over little c. But see, that's not the only thing that we can state here. What we can do is say, hey, let's forget the fact that we put H there. What if we were to put H from, say, A to little a, and we created a right angle there? And I'm just going to call it H here. Now we've got more sine equations we can come up with. The sine of B now is equal to H over C. And the sine of C is equal to H over B. Similarly to the previous investigation, multiply both sides by C, multiply both sides by B. H's by themselves, which means if both of these angles equal H, both of them equal each other. And then I can divide both the right and the left by B, and both the right and the left by C. Which means now the sine of B over B is equal to the sine of C over C, which we previously just said was the sine of A over A equals the sine of C over C. So if they both equal the sine of C over C, then they equal each other. And this is one way in which to express what's called the law of sines, which this doesn't work for every triangle. There are some cases where the triangle is created in such a fashion that it's so warped that you can't actually draw a right angle dropped from each side. This is the kind of triangle in which you can. I'm not going to talk about those cases today, but what I'm going to do is I'm going to go through some of the previous homework assignments for law of sines where, hey, this is an option. Let's see if it actually will work something out for us. So I'm just going to have off to the side law of sines, and it takes on it manifests itself in two different equation loops. The first one is just like we saw. The second one is when they flip it. I don't know if there's a reason for them talking about the reciprocals as also working. But yeah, of course it does. Now, law of cosines, I'm not going to dig into that too much, just because I want to make this video not lengthy. The law of cosines has three different three different parts. Let's see if I can drag this out of the way. So these are the three equations for law of cosines. And what this does is it says, hey, if you have significant angle information, law of sines is good. If you're kind of depleted on angular information, but you have information about the sides, then this is going to be the one you want to go with. And law of cosines, as you can see, is going to be created by using the Pythagorean theorem or alternate versions of the Pythagorean theorem. So I'll just leave it at that. And what I'm going to do is go through a few of the problems from the last night's assignment. So when you look at number 3 from 5.6, I trusted that you guys took the z, put it to the opposite side of the triangle, and you tried solving for all the parts. Or at least the parts in which gave you the area to that triangle. What if we wanted to solve for, say, A, B, and C? Okay, so I'm just going to call this is like the A, this is like the B, and this is like the C. So then this little one here is A, this little one's B, and we know that this is C. If you've got that information, now we can say, okay, which of these would be good to test out? And one of the ways in which you can process sine of which one of these you should use, law of sines versus law of cosines, is, do you have enough info about diagonals? So, the B's, you've got exactly one piece of info. The C's, you've got two pieces of info. We therefore should be able to say that the sine of C, which is 50 degrees, divided by 7 equals the sine of B, which is 80 degrees, over B. We can solve for that opposite side B with this equation here. So if I'm ignoring the fact that it's asking you to solve for the area of this triangle, and we're saying, hey, is there a way to solve for all the missing pieces? Yes, you can do it this way. So what does B equal? B equals 7 times the sine of 80 degrees divided by the sine of 50 degrees. I just did the proportion. Sine of 50 should be over here, but you divide both sides to solve it. All right, so it's 8.999. So you can ask yourself the question, do you have YZ as equaling approximately 8.999? Because that's the answer. And that was a pretty simple way to do it. You didn't have to drop an altitude or anything. So now that we've got that this is 8.999, we could solve the opposite side. Well, actually, maybe we can't because we don't have this angle. Wait, we do have this angle. It's got to be 50 degrees, right? because 50 plus 50 plus 80 is 180. Actually, this is an isosceles triangle, see? Two bases. So if this is 7, that means this has to be 7 too. I'm going to confirm that though. The sine of 50 degrees over unknown, so we'll just call it, I think we called that, I can't remember, A, B, C, we'll just say A, equals sine of 50 degrees over 7. Well, yeah, they're proportions. Top's the same, therefore the bottoms have got to be the same. So this is 7 as well. Now, what would it look like if we were to employ the law of cosines to one of these? Well, that would be more appropriate if you had side information. So normally, if you have at least 2 sides, like number 4, you would want to use it that way. So if we check number 4, you've got a side of 2, 3, and then 50 degrees. So it kind of just, it takes into account how you talk about which angle represents the A, the B, and the C in the formula. So right now I'm thinking to myself, I've got these 2 sides, which would be little a and little c, and I have the 50-degree angle for the B. So I have to use the cosine of B formula in order to solve. So B squared, that's the unknown right now, equals A squared plus C squared. And look, they leave out any trace of the B on the opposite side of the equation, which is exactly what we need in order to solve this thing. So 2 times A times C times the cosine of B. You plug in the information you have. A is 3, B is 2, or I'm sorry, C is 2. And then you square root that. And then you come up with a decimal approximation. And you get 2.299. All right, now I didn't totally solve any of these for you guys. What I wanted you to do is, what I wanted you to see was that, hey, I can find a total unknown side here by just doing this. Now, if we're solving for the height and we're trying to find area, there's a completely different formula than what's given here. I'm going to let you guys investigate that on your own. But you can still, if that's the case, use the altitude drops down, you've got right triangles. And in fact, you could use this maybe even more to your advantage to actually solve for it. Let's say you wanted to drop down here and you're like, oh, I don't know what the base is. I could find the base really quick versus finding parts of the base and then adding them together. So anyway, check out the problem set that I posted. Use law of sines, law of cosines the best you can. If you find yourself just getting stuck completely, don't just give up, but use the strategy where we talked about 5.5 and 5.6, where you drop an altitude and solve it with right triangle trig. All right, thanks for watching.